All right, the next example that we have here is example 2. Find a parameterization for the sphere of radius r centered at the origin and then at a point. So it's really two parts here. First, do the sphere of radius r centered at the origin and then change the center to a point ABC. So the nice thing about parameterizing a sphere or any portion of a sphere is we can simply use spherical coordinates as our, pretty much that will get us 99% of the way there. So let's quickly recall spherical coordinates. So in spherical coordinates, we have the following conversions from Cartesian to spherical, or spherical to Cartesian at least. X is rho cosine theta sine phi. Y is rho sine theta sine phi. Z is rho cosine phi. Okay? So, essentially, these equations right here are going to be our x, y, and z components of our parameterization. So there's two options here. Option 1 is to keep things in terms of theta and phi and just write your surface parameterization not using u and v and writing it as just keeping them the same. Now notice here, rho in this case, because of this problem, it's a sphere of radius r. This rho is not going to change. So for us, we're going to let r equal rho. So this would be r cosine theta sine phi, r sine theta sine phi, and r cosine phi. If we want the full sphere, remember that theta has a maximum range of 0 to 2 pi, whereas phi has a maximum range from 0 to pi. If we wanted like the upper hemisphere, then phi would just be 0 to pi over 2. If we wanted maybe just the half of the sphere with positive y value, then this would be theta from 0 to pi. So you have to think about what portion do we want like in a different problem. But for this problem, we want the full sphere, so we're going to use the maximum available range for each theta and phi. So that's a perfectly reasonable thing to do. Some people really prefer using these things. For me, I generally like using u and v to keep it, because there do come times where sometimes it seems like you're mixing coordinate systems together, especially when you're doing a surface integral or a triple integral, and sometimes you can get a little hairy. So I like using u and v, but there will be times where I don't use u and v. So one of the most important things or skills to have in mathematics is you are nimble or adaptable with your notation. You shouldn't be too fixated on the individual letters themselves, but rather the relationships between them and what they represent. So I do like to switch things around just to keep on my toes a little bit. So this would be essentially the same parameterization, just letting, doesn't matter which one you pick, but I always kind of stick in the same sort of idea here where I use u as my theta and v as my phi. And then our range would be for u comma v, 0 to 2 pi, Cartesian product with 0 to pi for the range of v. So right there, either one of these gives us a parameterization for a sphere of radius r centered at the origin. So like the first half of this problem is done. The second half, what about at the point p equals ABC? Well, what we can do here is if we just imagine taking every single point on the sphere and just moving it in this direction. So for instance, if we think of our coordinate system, here's our sphere centered at the origin. And then let's say my point ABC is somewhere over here. Or actually, let's do it down here so I can actually move this. So right there. So there's my point P equals ABC. So what I can do here is imagine taking a vector. This vector is really the vector ABC. It's the position vector to the point P. It's the vector O to P. What I can do here is at every single one of these points, for instance, I can just take a sample point right here on the sphere and imagine taking this vector and lining it up there. And this is going to create for me, let's go ahead and just move this off to the side for a second. We don't need that. That's going to tell me where to move this blue dot. That goes there. And I can do the same thing with another point. I can say, okay, what about this point? Well, this blue dot here will go to that blue dot. And I can do this for all of them. I can just take all of these points and add to this point, or to that position vector, this vector ABC. We get this point. And if you actually do this, you can see that we will actually get a sphere. Might be hard to see at first until you kind of convince yourself of what's going on here, but we will actually get a sphere. So I'll do like, oops, I will do one more. Probably I'll do like the North Pole. All right. And maybe I'll do, that's good enough. That's good enough. So then what you end up seeing here is this whole sphere just gets translated by this vector. It just translates it. So really, all we're going to do is since, so let's go ahead and keep that back in here. That's this vector ABC. Essentially, what we can do is take our parameterization, which is, we'll just copy this parameterization right here, and effectively, all we're going to do is add to it. So instead of just R, we'll have A plus that. We'll have B plus that. And lastly, we'll have C plus that. And that will be our translated. So maybe I'll call it something else, G of UV. So really, G of UV, if we just want to translate our R of UV, we can just take R of UV and add to it our translation. So if we want to center it at O to P, we would just add the components of O to P to R of U. And our domain would be exactly the same. So we can think about this as just moving its whole center, translating it.